Hello, everyone. My name is Jiali Zhang from Missouri University of Science and Technology. Today, I'm excited to share with you our research on subspace interpolation and indexing on Stiefel and Grassmann manifold as a lightweight inference engine. This research is collaborate with Dr. Wenqing Hu from Missouri University of Science and Technology, Dr. Zhu Li and his research group from University of Missouri, Kansas City, and Dr. Tiefei Jiang from University of Minnesota, Twin Cities. And here's our table of content. So I will start with an introduction of our motivation of the research, and then I will talk about the methodology we proposed, and then I will introduce the lightweight inference engine built upon the methodology we proposed, and then as the experiment result, and finally we will have the conclusion. So first, the introduction part. In the realm of high-dimensional data analysis, traditional subspace selection algorithms like PCA and LDA have played a fundamental role. However, they often couldn't capture the nonlinearity and the local variation inherent in the complex dataset. Our motivation was to address these limitations. While nonlinear methods and DNN offer solutions, they come with high computational costs, and this led us to develop the subspace indexing model with interpolating, or SIMA-I, which is the novel, more efficient approach. So let's dive into our methodology behind the SIMA-I. This figure illustrates the core idea of our approach. So basically, the SIMA-I is constructed in two primary steps. The first step is we start by creating a piecewise linear model that's aware of the data's affinity under the given partition. And then in the second step, it involves interpolating between these models using what we call the center of mass calculation on Stiefel and Grassmann manifold. So here's the first step of SIMA-I. The LPP aims to find the linear transformation that maps the high-dimensional data to a low-dimensional space. This transformation is designed to preserve the local structure of the data, meaning that if you have the two dataset points that they're close to each other in the high-dimensional space, then should remain the close in the reduced space. And here's the example of process of LPP. Given the data set, we will first apply the techniques like the PCA to conduct the dimension reduction, and then we will apply the KD tree based on this partition to divide them into non-overlapping subsets. And finally, we will construct the low-dimensional embedding matrix by the LPP. So for the details of calculation and more comprehensive explanation, please refer to our paper. As we talked about before, the W matrix is something we care about. The W matrix here provides a low-dimension representation of our dataset. In this case, the column space of W is what we care about. So we can assume that the column space of W is an orthonormal basis. So this kind of matrix belongs to the Stiefel manifold. As an example, If we're interested in the signal recovery using low-dimension PCA embedding, the projections we calculated will be on the Stiefel manifold. And here's the definition of the Stiefel manifold. However, for classification tasks, the exact distance information is less important than the label information. And in this case, we need to use the Grassmann manifold as we define here. The Grassmann manifold is defined to be the quotient manifold of Stiefel manifold divided by the group of the orthogonal matrix in dimension D. After introducing the concepts of Stiefel and Grassmann manifold, let's explore how to calculate their center of mass. Given a sequence of matrix W1 up to Wi on the Stiefel manifold and the corresponding ways, the Stiefel center of mass with respect to the distance is defined as a matrix that minimizes the function given by the weighted sum of squared distance. As you can see, the formula we have here. And similar to the Stiefel center of mass, the Grassmann center of mass with respect to the distance on Grassmann manifold is defined as the equivalent class that minimizes the function given by weighted sum of squared distance. So let's explore how and when to use the Stiefel and Grassmann center of mass for carrying out the interpolation. As you can see in this figure, suppose we have three different subsets, C1, C2, C3, with means M1, M2, M3 in the training set. In the first scenario, we have our data point X is apparently close to M1, and thus the low dimensional embedding of X is taken as the W1 transpose X, where W1 is the LPP subspace based on C1. But when it comes to another scenario where our X has the approximately same distance to 3 category, our embedding matrix F is taken as the Fx equals to WC transpose X, where the WC is the Stiefel and Grassmann center of mass for LPP subspace model, as what we defined before. All right, so after introducing the LPP as well as the interpolation, we can combine them together to develop our semi-algorithm. And for this algorithm, our input will be the dataset, the corresponding affinity matrix, the testing data point, the threshold ratio, the depth of the tree, parameter k. And the first, we will use the PCA and KD tree to decompose our dataset into different subsets. And then for each of the subset, we'll calculate its mean and its LPP embedding matrix. Next, we will sort the distance in ascending order, and then we'll determine the I based on this criteria. And then we will obtain the embedding matrix or their corresponding subspace. And then we will find the center of mass on Stiefel case or Grassmann case according to the definition and theorems we talked about in previous slide. So our output will be the low dimensional embedding Fx equals to WC transpose X. Now I'm going to show how we can use our Sigma-I construction to build a lightweight inference engine, LIE. The LIE is a novel inference framework that builds upon our Sigma-I. This figure shows how a scenario where the Sigma-I combined with the pre-trained learning model and the data manifold. But this is one typical case of our LIE application. In addition to use the pre-trained labels, the LIE can also use the original natural label that the data has. But for the first scenario, the LIE with the pre-trained model label, this approach enables LIE to directly map the complex data to classification labels, utilizing the advanced feature extraction of this model like DNN for efficient inference. And for the second scenario, the LIE with natural label, this method allows the LIE to operate as an independent learning model. And what's fascinating is that this it achieves the classification accuracy comparable to standard model like DNN, but with significantly reduced computational complexity. And you will see it in the experiment part later on. And now let's dive into some insight of the LIE offers. So first, unlike the deep, complex structure of traditional neural network, LIE is more like a shallow neural network, having a wide first layer with ReLU-like nonlinearities. And this design marks a significant departure from conventional deep neural network. Second, LIE represents a shift from a deep to wide but shallow neural network architecture. This is especially critical when integrating the LIE with pre-trained DNNs. And third, LIE stands out with its unique activation function and feedback circuits, which are not typically found in standard networks. Lastly, LIE serves as an alternative way to NTK-wide network. So it's not just a tool for efficient inference, but also help us to gain new insight into the interpretability of the deep neural networks. Moving on to the experiment part of our presentation, we conduct 3 different experiments using LIE model we previously developed. So our first experiment involved PCA recovery for SIFT dataset. We used the SIFT dataset where each of the data point has 128 elements. And for this, a total of over 10 million sample points were utilized with a specific selection for training. And the data were projected onto a 16-dimensional space using Stiefel metrics. By dividing the dataset into 8192 subset and employing PCA embedding metrics, we compared the recovery efficiency between the standard PCA and our Sigma-I techniques. So as you can see this figure, it shows the comparison of PCA recovering errors, where the blue is the benchmark case using PCA recovery with errors sorted from the low to high, while the red part is using the Sigma-I. And the results were compelling. The Sigma-I method showed improved efficiency for about 93% of the data points compared to the benchmark PCA. Next, we focus on the nearest neighbor classification with semi-I on the MNIST dataset. The MNIST dataset with its training and testing set were projected onto a lower dimension subspace using PCA. The training data was clustered by KD tree and LPP embedding metrics were computed. Here you can see the table. We use the table to compare the classification rate between baseline and semi-I method. And here we performed two experiments. First, if we take the KN to be 1 for baseline method, the classification rate is 93.58%, and for semi-I is 95.55%. And if we take the KN to be 75, for baseline method, the classification rate is 87.52%, and for the semi-I is 94.21%. The result shows that the semi-I method consistently outperformed the baseline method in terms of the accuracy, even when compared with a pre-trained LNAV5 model. Lastly, our third experiment focused on the classification of PCA embedded phase images. Utilizing a dataset over 400,000 phase images, we proceed and standardize these images, then apply the PCA for dimension reduction. We conduct the test at different dimension levels. Here are two graphs to show the variance explained by 256 and 128 dimensional PCA embeddings for phase dataset. And here comes our result. As you can see in the table, the classification rate in two methods are pretty close. But compared to the neural network, LIE has a simpler architecture. And this demonstrates that our semi approach is effective and it can handling the large-scale dataset, and also its potential in building an efficient and accuracy classification systems. So the last part, to conclude, we introduced the semi-I, an inventional approach for a high-dimensional dataset, leverage the power of Stiefel and Grassmann manifold. We also developed the LIE, a lightweight but powerful engine for data inference, offering a viable alternative to more complex DNA. We also conduct experiments across different datasets to show the effectiveness of our approach. We believe that our work opens a new way to understanding and interpreting the DNA, especially in how we can simplify complex model without compromising on efficiency and accuracy. Thank you all for your attention. I hope this presentation has given you valuable insight into our research and its potential impact on the field of data analysis. Thank you.